So okay, first thing, good. Second axis is good. Is the Hertzsprung-Russell diagram. What it is, and then what are the stars doing? So I think first I should talk about life cycle. Second about the supernovae classification. Since if there is 1A, you would expect there is 2A or 1B or whatever else. So there must be a reason to call them 1A. And then significance for cosmology. And H-naught measurements. So someone said that a star is just self-adjusting ball of baryons with this coupling constant. The shortest definition of the star. Self-adjusting system of baryons. It is self-adjusting because basically a star is a ball of gas which has got outward pressure of radiation, the sigma T to the 4 style, and then you've got an inward pressure of gravity of all those masses that are pulling against. And it's in the hydrostatic equilibrium, which is like which is just the balance between those two forces. I can show you a nice picture. In anything of between 1 solar mass and about 10 solar masses, or even less, you would start off with just pure ball of hydrogen and some other elements which are metals. So you've got just hydrogen which changes into helium in the core. Because there is a difference in mass between helium and hydrogen, roughly, that's what happens, because hydrogen is just 2 protons and 2 neutrons, or helium is just 2 protons and 2 neutrons. Then the difference in mass, c squared, is the energy that you are taking outwards. And this is what is counteracting against the pressure of gravity. And there are different timescales. There is the nuclear timescale, which is just connected to the efficiency of the nuclear burning, and because the nuclear burning phase is going to take 10 to the 10 years, it scales as 10 to the 10 years to the 3rd power. So that if the star has got the same mass as our sun, it's going to take 10 to the 10 years to go through this nuclear phase. If the mass increases, if it's like 10 times more massive than our sun, then it's going to live 1,000 times shorter. So that it's going to be actually 10 to the 7 years, which is just 10 million. So our sun gives us 10 billion years, 10 to the 10, and it's at the moment roughly halfway through this phase. This phase on the Hertzsprung-Russell diagram, which could be here labeled as temperature, for instance, log of temperature. And here you could have log of many things, for instance luminosity. You've got the main sequence where just the star where the star starts and sits there for a long time in its evolutionary period. And then as it runs out of all the hydrogen in the core that you have been burning, suddenly the core undergoes collapse, and it doesn't support anymore. Again, it doesn't have any support against the collapse of those parts that are surrounding it. So it contracts. But as it contracts, it heats up, and because it heats up, you reach enough temperature for the triple alpha process to occur, so that you get 3 alpha nuclei of helium connecting together to form carbon. I think this is the first element. Yeah, 3 He goes into carbon. Actually, that was 3 times 4 is 12. And this is the next element that you're just producing in the core. And now the star looks a bit like onion with hydrogen envelope, hydrogen into helium, and then the hot helium into carbon core. And this is this ignition of helium into carbon is called the helium flash. So that then the temperature decreases because it has been increasing all the time as the star has been contracting. But then, as you get helium flash, it starts producing more radiation in the middle again, so that the star puffs up and it becomes a red giant. And this is when its radius increases massively, but because it increases, then the same radiation is spread out onto a larger surface, which makes the temperature decrease, so that the star from being a sun-like bit becomes something of roughly that size. Just like this is the red giant phase, and when in our solar system the sun is going to become a red giant, it's going to hit the orbit of roughly Mars, so that the Earth would be entirely engulfed into by the outer atmosphere of this star. I mean, ask me questions if you don't understand anything, because it's pointless if I say something that you don't understand.
That's right.
Ah, okay, that's good.
Why doesn't it have to be log of L with respect to log of T?
Oh, it doesn't have to be. I mean,
I'm okay with temperature, but why luminosity, for example?
well, luminosity scales. Okay, so it doesn't have to be log of L, but it could be log of mass.
I get it's not. It seems to me that L depends on temperature.
Yeah, yeah. Okay, so it's better to log n, because I don't remember all of that by heart. But you could put a lot of those different values on the same axis. And then depending on the mass, obviously, if it's been massive enough, then it's going to continue to burn other elements. So you again get contraction as you run out of helium. This is the asymptotic giant branch. And then you start burning carbon into neon. So it's 12 carbon plus 12 carbon going into 20 neon plus 4 helium goes also into 23 sodium, goes also into magnesium. But this requires energy in the core of about 10 to the 9 Kelvin. Or a bit less than 10 to the 9 Kelvin. As you run out of carbon, then you start burning oxygen, if you're massive enough. So it actually goes all the way here, but every single phase takes less time, because the burning is much less efficient. The idea behind nuclear burning is quite simple. Basically, every single nucleus, this should be Z, which is the number of protons or neutrons, and this should be energy per nucleon, also called the binding energy. It does something funny at the beginning, but then it roughly increases until it goes quite flat. So this is the energy of the binding between protons and neutrons in the core. What's the difference, basically, between having 4 separate protons and neutrons and putting them into the core? And actually it turns out that as you add up, like the proton would have 938 megaelectronvolts. So you add up 938 megaelectronvolts, 938, 935, 935. This gives you a number, but if you put them all together into the core, it's going to be less, because some of that energy has been expended onto the binding. And that's why it is energetically beneficial for them to be bound. Otherwise, if this energy, if they had more energy when they are bound than when they are unbound, it would not be a bound system, because it would constantly try to gain equilibrium by having less energy. And that's why this diagram is important, because you start with like hydrogen, helium, and going all to all the elements, and with every single step further with Z, you get higher binding energy, which means that it is more stable. But then you reach the maximum at 26. We've got 26 protons, this is iron, and that's the limit of fusion. Beyond that, it doesn't make any sense to fuse, because if you fuse two elements, say 2 atoms of ferrum, the next element is going to have smaller binding energy. So it doesn't make sense, so it would stay the same. But as the star has expanded so much, and you really don't have anything else to burn, you need to provide radiation. So this diagram would have to be updated. And it would really look like this kind of onion structure, as they call it, with, I just copy hydrogen to helium, then, yeah, I know, circles, it should be circles, because it's a sphere. Then it goes as helium to carbon and oxygen. Carbon and oxygen goes into silicon. Silicon goes into ferrum. And you've got a ferrum core. And then what happens? When you've got just a ferrum core, you can't have any more fusion reactions, because it would be energetically impossible to make it. You would require energy rather than release energy. And that's why at this moment the reactions stop. Because the reactions stop, everything suddenly collapses. But the only thing that collapses at the beginning is just the core, because all of those envelopes above it are happily burning. I mean, hydrogen has got nothing, there is nothing wrong with all those phases before ferrum. So in this star, all those reactions are constantly happening. The only problem is in the core, that the core cannot have any more reaction, and that's why it collapses. And the core made of carbon, of ferrum, of iron, suddenly collapses.
So it collapses because it doesn't emit radiation anymore.
Basically because it is impossible for it to emit radiation. It could undergo fission, but there is too much pressure for it to do so, because it's pressed from everywhere. Like above you, there are hundreds of millions of kilometers of all those layers. So it's a huge pressure that you're against. So the only thing that you can do is collapse, because there is still a lot of empty space. I mean, I say it is a core, but you know what is the structure of atom? Structure of atom is such that you have got a core, atom nucleus, and if you were going to compare it to the size of a theater, the nucleus would be just the size of a ping pong ball, and the atom would be the size of the entire theater. So it's actually a lot of empty space. And that's why you can just shrink, removing all that empty space. And just take, you just take one nucleus next to the other, and that's how you create a neutron star. Because then it's supported entirely by Fermi degeneracy pressure of neutrons. And Fermi degeneracy pressure, for those who don't know, is just a pressure which is exerted by fermions. Fermions are particles which have got a spin half and statistics such that it doesn't allow them to sit in the same state. You can only put two on one energy level, and at zero temperature they just stack up. That's energy, and this would be like particles. You can have just two because they have spin half, so there can be only up and down on every energy level. And you just feel all the energy levels which are quantized because it's a quantum system. And neutrons stack up in exactly the same way until they hit Fermi energy. And then the star is not supported anymore by gravity. It's not supported by the balance between gravity and radiation, but it's supported by the neutron degeneracy pressure, which are yeah? You can derive it if you like.
Mm. So that was a red giant.
Yes, it was a red giant, and then it goes into an asymptotic giant phase. I guess supernova would be. It depends on which part of the star you're talking about. Because if it was about temperature, it would go somewhere like that, the supernova phase. But when it goes to mass, it will go that way, because you lose all the mass. But then just it stops being a star, so it's kind of pointless to talk about it anymore.
So it collapses, then it explodes, and if it's got enough mass, it becomes a supernova?
No, that's all that I have been speaking up to now is about high massive stars, and when you are able to reach those phases of burning up to ferrum, this is the core collapse supernova. So this is the process which drives the supernova explosion. And the interesting thing is that the explosion itself is not an explosion, it's actually driven by neutrinos. By neutrinos for which the matter surrounding it is so opaque that they are driving the runaway explosion.
So what exactly happens when this core collapses?
That's the interesting thing. So you get a lot of transformation because you have to have neutron degeneracy pressure, and as you know, ferrum has got quite a lot of protons. You can't have protons in the neutron star. What do? You undergo inverse beta. Is it inverse beta that you connect proton and neutron to form proton and electron to form a neutron?
Yeah.
That's how you get rid of all the electrons that you had in the ferrum. But this releases neutrinos, and those neutrinos are happily escaping, and indeed what you are left with is just a neutron star. A star composed chiefly of neutrons, which are supported by the degeneracy pressure. And I am speaking of that case not up to infinite mass, because the degeneracy pressure surely has got a limit. There has to be a limit for that degeneracy pressure, and there is one. The maximum mass of neutron star, sorry, it's illegible. So maximum mass is roughly 1.8 solar masses. And it also depends, because it depends whether the iron is going to be static or rotating. And I'm going to talk in a minute why we don't really see a static nuclei. That's a very interesting topic. I mean, I could talk about it for a few hours, but I just wanted to give you an overview. So these collapses, those layers do not have any support. So until this information about the collapse reaches them, and it's quite a long distance, the information travels with the local speed of the speed of sound. So until they don't realize that they are not supported by anything, they don't collapse. And this happens on the time scale of as long as it takes for the sun for light to go from one end to another. So this happens during the few seconds. This happens during about 10 seconds. The collapse of the core into the neutron star. And it becomes a neutron star only if the mass is smaller than that. If it's supermassive, then it collapses further and you get a black hole. And if it's much less mass, then you wouldn't really be talking about ferrum burning, because you wouldn't have enough mass. So the supernova this core collapse supernova would only be created when you have got this onion-like structure in a massive star, and it triggers an explosion, not because it explodes from inside, but rather as those layers get the information about the fact that they are not supported by anything, they fall onto the core, and then the released gravitational energy is about 0.1 of the mass of the neutron star times c squared. So it's about 10 times more efficient than the nuclear energy burning. That's released just because you are releasing all the energy of of the core when you're contracting. And this energy is roughly comparable to the energy of the gravitational pressure, which is why that energy plus the energy of the neutrinos bounces those layers away, and then you get an explosion. So it's not the explosion because something explodes inside, but rather explosion because all those layers bounce off. And they are bounced off by the energy released due to the contraction of the core.
So if it's not massive enough, it doesn't happen. And
No, it doesn't happen.
Work.
No, because if it's not massive enough, like entire star, you wouldn't get into the phase of burning silicon into iron. And then you get the thermonuclear explosion and everything explodes. And also, it's interesting that then, because of all those neutrinos, you get a lot of different processes. I gave a very sketchy picture. You get a lot of neutronization, for instance. And this produces a lot of elements which are much heavier than iron. But this is only released during the process of the explosion. And that creates all those atoms beyond here. That's why all heavy elements have been created in supernovae. Because there is no other way to create them. As you see, by nuclear burning you can get only ferrum. And as we know, we have got many other elements. And there is no other way of creating them than in the supernova. So it's quite interesting to think about it. That there would be no nuclear power plants without supernovae. Because we wouldn't have any uranium whatsoever. And all the other elements. Yeah, there is a lot of interesting processes like photodissociation of nuclei, which I mentioned, that you just destroy part of this core by the fact that it's being pushed. And then you also get the neutronization. And then there is an interesting thing about classification. Because that's just one type. And there is also another type, which evolutionary is entirely different. This type is the 1A, because this was, for instance, 2 or any other. But this was the core collapse, which is type 2. Because a star can get any mass, as long as the core is not bigger than the mass of the black hole, and still, if you get a black hole, you still get a supernova. You might just get a different type, so type 2Pa or whatever. But overall, the core collapse is type 2. And this is not the one that we are observing, because you can get such a wide range of the masses of the star. There would be no unification as to when you actually get an explosion. It might have a wide range of different luminosities, the output luminosities of the supernova, and that's why it's useless for cosmology purposes. But there is also another type of supernovae, which occurs when you have got a binary system of stars, and that's 1A. Find a nice picture of it. It's the thermonuclear explosion, which is entirely different mechanism. So I don't actually need that anymore. So this was a very massive star, say, mass bigger than 10 solar masses. But what if you have a pair of stars, for instance, a red giant, and then orbiting it, well, they are both orbiting each other, a white dwarf. A white dwarf is a similar system to the neutron star, but this one is supported by the electron degeneracy pressure. Because white dwarf is also a degenerate star. Basically, I mean, in order to explain all that, I would have to just tell you about all different fates that stars can have depending on their mass. Very low massive stars are going to start on the main phase, sit there for a very long time. Perhaps they would be able to go into the helium burning phase. They would expand. And then, because they would be not massive enough, they would actually get rid of all the outer envelope. And the only thing that would be left would be a collapsed core in the form of white dwarf, which has got a radius of about 10,000 kilometers, the size of the Earth roughly. And it goes down here. So these are the white dwarfs. And it looks really nice because all the planetary nebulae are basically such objects. Oh, there you actually have a movie of that. Why do you have to start around it? Ah, okay, they're showing just a huge system. It doesn't have to be like that. That's quite an extreme case, actually. But this part is universal. So you just get an explosion and depletion of the external layers, and that's how you would expect it to look like. Why? Yeah, that's how you expect it to look like. So this is the white dwarf star inside. And these are the layers that have been thrown away, the outer layers of the red giant. And that's how our sun might look like in 5 billion years, basically. Because the red giant phase is much quicker. It's taking just about few millions of years. Then, if you are a more massive star, it takes much less to reach the red giant phase. Then, as I say, you might start burning helium into carbon, carbon into something else into something else, and then you undergo a supernova, and you're off. A very low massive stars might just become degenerate and go straight here. Some of them also populate this region, this blue supergiant, which goes straight through here, and then they go off. So these are like 3 different cases. So this would be a star coming from, for instance, the mass of the sun, and this would be a remnant of such stars. So you could imagine that you had 2 stars which were same as our sun. One of them was a bit more massive, so it expanded first into the red giant phase. The second one was still main sequence, and then the red giant expanded all the outer layers and it became a white dwarf. And then this one expanded into the red giant phase. So now I have a white dwarf and a red giant. This could be a way that you could actually get the system of white dwarf and red giant. And then, because they tend to be very close system, because you lose a lot of distance, for instance, due to the friction of the medium once this one has expanded the layers. This star usually fills the Roche lobe, and then it starts accreting mass onto a white dwarf. And then the best thing about that is that this is not an explosion once you get a lot of mass accreted around the white dwarf, and it produces X-rays and everything. But X-rays are produced just from the accretion disk, not from the point where they're touching the surface. It's even more interesting when you have got a nuclear star. But basically a white dwarf, the mass which is supported has to be lower than the Chandrasekhar mass, which is about 1.4 masses of the Sun. For the neutron star, it was less than Oppenheimer-Volkoff limit, which was about 1.8. But neutron star is also much smaller, so I'm talking about the simple case of the white dwarf. And when you get all the accretion and the mass accreted onto the white dwarf increases beyond the mass of the Chandrasekhar mass, you get thermonuclear ignition. You get carbon ignition, then the thermonuclear runaway, and the star is completely destroyed and it explodes as supernova. And because it always has to just go above Chandrasekhar mass, you get very similar distribution of luminosities. They are not the same, but they are similar. The span of such luminosities, the light curve of such supernova, this would be light, luminosity, brightness, whatever, and this would be time. Might be like that, so it would be log actually. So this could be 10 to the, let me be more specific, 10 to the 40. And this one could be 10 to the 41. And it's still supernova 1A. The main difference is that it seems that the width of those curves scales with luminosity. So that even though there is a vast there is a vast difference in different types, in different cases of those white dwarfs accretion, and there might be different energies of the explosion depending on particular components, for instance, of the matter that was accreted from the red giant, and also on the parameters of the system itself. Because this thermonuclear, it also matters what are the elements which are accreted onto the white dwarf. Then you can still scale it, and you can still tell what was the maximum luminosity. Because many people call it a standard candle, assuming that all supernovae 1A, this is 1A, assuming that all 1A have got the same brightness, but they don't. They have got a range of brightness between 10 to the 40 and 10 to the 41 of watts. And then the only thing is that they are standardizable candles, so that you can standardize them by measuring the width of the light curve as it brightens up, reaches the maximum, and then it fades. You can measure the width of this curve, and the width of this curve tells you what is the luminosity of the object, the absolute luminosity of the object. And that's the most interesting thing for cosmology.
Well, I have candles.
A candle.
Yeah, but in this sense, in the case of stars.
In the case of stars, they called it a standard candle because they thought that if you have got a candle which has got a known brightness, you know what is the brightness of like a light bulb. They thought of it just like a light bulb, that it's like having a 100-watt light bulb. If I know it is a 100-watt light bulb, if it's very close, it's going to be very bright. If it's further away, it's going to scale as 1 over r squared as the distance decreases, because your power has to go into a much bigger area, which scales with r squared, because the area is r squared. You understand that? So if you would say that if it is 100 times dimmer, it's 10 times further. If it's 10,000 times dimmer, it's 100 times further than the standard candle. You obviously have to know where is the first candle which you are measuring it against, because you are just comparing the brightnesses. And that's why they are called standard candles, because many people thought that these 1A supernovae are just like that, because it seemed that you just have to overtake the Chandrasekhar limit and voila, you explode. And you get always the same brightness. So you know what would be the brightness. They thought that it's just one brightness, say, of 10 to the 40, for instance, watts, just like light bulb, but many times more bright, and much brighter. And they thought that if they know what is the absolute brightness, then okay, if we can find supernovae somewhere which we know how far it is, for instance, our Milky Way or anything that we can measure by different means, like the parallax measurement, because this is like the cosmic ladder. And they call it a ladder because there are different ranks on the ladder, and you can't go to the other one without knowing the first one. The first one is parallax measurement. So you just see that as you go on the orbit around the sun, that's the Earth and that's Sun, you will see that a nearby star moves with respect to the background of very distant stars. So you measure this angle, the parallax, and simple trigonometry tells you what is the distance, knowing this angle. That's the most simple method. But unfortunately, it doesn't work for anything that is that is like beyond 1,000 light years or something like that, because then the angle becomes impossibly small to measure. The position of the star, we just would be unable to measure the change of that position. It seems not to have moved by a pixel, but we would say that a pixel is just an error in measurement. So assume that by parallax measurement, we know that the Magellanic Cloud is it 500? I think it's 500 kiloparsecs. So you know, because of the distance measurement, but before I said that it's, so the next step are Cepheids. So we go with parallax to a nearby Cepheid. A Cepheid is a star which pulsates, and the period of pulsation tells you what is the luminosity. So if it pulses much quicker, it's a smaller luminosity. If it pulses very slowly, like expands and then contracts, so it changes the luminosity, it's going to have a bigger luminosity. So we know what is the absolute luminosity, and from parallax you go to Cepheids. Because, for instance, you measure the parallax of a star which is in the same group as one Cepheid. So by knowing what is the distance of that star, you know what is the distance of Cepheid. And then from the Cepheid, you can go to another Cepheid, for instance in the Large Magellanic Cloud, which is a satellite galaxy of our Milky Way. And then, for instance, also measuring Cepheids, you can go to the nearest galaxy, the Andromeda Galaxy, which is already 2 million light years away.
And how do you measure the distance to Cepheids?
To the Cepheids, because you have measured a parallax of a star which has got the same distance as Cepheids. Because, for instance, we know that they are bound in the same cluster of stars. So it's not accurate. I mean, it's plus, already in parallax, it might be plus minus 10 parsecs, but a parsec is nothing. A parsec is just 3 light years. So 10 parsec is just 40 light years. 40 light years for us seems like a lot, but in cosmological time scale it's actually very small.
And
then from Cepheids, you know, you can go up to this Large Magellanic Cloud, and then, for instance, in the Magellanic Cloud, you get a supernova explosion. So you already know how far is the Magellanic Cloud, and you see a supernova.
No, but how do I know how far it is?
What? The LMC? Because you have measured the Cepheid.
So how do I measure the Cepheid?
I told you. Because you have measured the parallax of a star that is next to the Cepheid.
In my galaxy?
Yes.
But then in this other galaxy?
Because you know how far is the first Cepheid that you measured, because you knew the parallax of the star which is nearby, you have scaled the Cepheids.
Scale. No, I don't understand.
A Cepheid is also a standard candle, so that by measuring the period, you know what is the absolute brightness. You measure the brightness, and you just use the distance modulus. So the visible one is the absolute one minus 5 of d.
Alright.
And d is the distance. So the further it is, the dimmer it seems to be. And that's why once you know this first, you know what is m, you measure small m, so it gives you d for these Cepheids. And then knowing the first Cepheid distance, you can compare the brightness of this one to this one. And this is how you go to this point. And then imagine that in the same Large Magellanic Cloud you get an explosion of supernova. So immediately you know how far away is this supernova. And this gives you a next step in the ladder. Because supernovae are so bright that they can be seen much further away. Cepheids are just like big giants, pulsating red giants. And so they have got a given brightness which it doesn't enable us to see Cepheids further than like Large Magellanic Cloud. But a supernova gives a possibility of measuring it much further away, because a supernova might have a brightness bigger than an entire galaxy. I mean, 10 to the 40 watts is massive. A star has got, our sun, I'm not sure if I have got constants, but the luminosity of our sun is many orders of magnitude less than that. Luminosity of sun is 10 to the 26. 26, 40. That's 14 orders of magnitude brighter than our sun. That's a huge difference. And that's why, if you know where is the first supernova, then you can go to then knowing this distance, you can just compare the candles, because now you know where you have put the first candle, where you have put the first light bulb. And then, by seeing how much dimmer is the other one, you know how far it is. And that's entirely separate to the Hubble law, because Hubble also noticed that those which are further away are also drifting much quicker away, because they have got higher redshift. That's because the universe is expanding everywhere, so the further away it is from us, the quicker it expands. And he postulated this law, which he just measured experimentally, that as you measure different galaxies, the redshift is a straight line, V and R. H naught is VR. V is H naught R, V R, okay. It's a constant relation. So the further it is, the quicker it goes away. And he just measured several galaxies, and they all seemed to be going away much further, much quicker. The further it was, the quicker it was escaping. And that's how he postulated the Hubble law, which is entirely separate from supernova measurement. Because supernova, once you know